And here we are. It's the Natural Science video lecture. Natural Science 116 video lecture 9. This is the penultimate video lecture, and we'll do new material today and then review, try to tie everything together next week before the exam. So we had finished talking about electricity, magnetism, and electricity and magnetism. Electricity is really the universal powered transport method. We can transport it over great distances. We can generate heat. We can actually get work out of it with electric motors. So that is very important to understand. And the level that we've treated it at is good for all of our prior and further discussions on transporting energy. So right now we're going to talk about solar energy. This is our last topic, solar energy. And let's get started. Solar energy. So first of all, what do we mean by that? We're talking about the light and the heat from the sun. And some of the applications we've already talked about, because the sun drives many things. So actually, if we were to make a list, it would be kind of fun. We could talk about the energy in our food as being solar energy. In as much as so-called fossil fuels are, oil and stuff comes from ancient plant matter that was converted into oil over geological time. We can also refer to oil as a form of solar energy, although that's usually not what we mean, right? But we also had the water cycle when we were talking about hydroelectric power. Of course, we had to mention the water cycle, and that's driven by the sun as well. So all of those things and more, and then the specific types of energy that we think of as solar energy with solar panels and things like that. I'll just put solar panels here. Will all fall under this heading as well. Okay, so it's a broad topic. Radiant energy from the sun. And remember, we had we had heat transfer. We didn't say energy, we had heat transfer by radiation. And of course, that was, if it comes from the sun, then it's that as well. So solar energy, radiation from the sun. And we know it's electromagnetic radiation, primarily. And we know that it's light, okay, from the sun. So the question arises, how much is that in terms of joules and watts and the energy ideas that we've developed? So how much energy are we actually getting? So the next topic, how much energy? How much energy is it? And to answer that, there's actually an experiment that one could do, and what I'll do is just describe it. How would we collect solar energy in order to tell us how many joules, how many watts are involved? So yeah, when I put after this question mark, I'll say joules / watts question mark. So that's what we're going to answer. And I'll start another board for that. So here's our experiment. In fact, you could do some version of this in your schools, because fundamentally what I'm talking about is the following experience. In the summertime, which we have coming right up now, you go into the backyard and there's a hose laying out in the sun, and you turn the water on, and what comes out of that hose? Very, very hot water, okay? So the rays of the sun will heat the water at a hose that's laying out and back on the lawn somewhere. So here's our experiment that is going to take advantage of that. I have to draw some kind of box here that faces the sun. And it can take more than one try. I need some kind of perspective here. Well, here we go. We have, there, that's a box, and we have incoming sunlight. And this box has a couple of features. It's filled with water. It has a black surface on top, maybe the water itself, or it could be a glass surface and the water could be dyed black with ink. Okay, we want to absorb a bunch of sunlight into this water here to indicate that the box has water in it. I'll have some blue here that says water. Okay, so we've got a water-filled box, and it has an area A facing the sun. Okay, the box is full of water, and let's just indicate that it has a thermometer in it. So as the sunlight heats the water in this box, we can record the temperature change with a thermometer. So area A, I'll write mass. So area A facing the sun facing the sun. Okay, surface area A facing the sun, that's right there, cross-hatched. And then we'll say, I'll have these bullet points, mass M of water in the box. Mass M of water in the box. We've got a thermometer. Thermometer measures temperature change. So we have a certain temperature, room temperature water, we take it out, put it in the sun, and we start measuring the change in temperature as that goes up there. How about we add a little more color to the mix? And we've got some thermometer here. We've got this incoming radiation, like that. And that's our experiment. We have a clock to time how long it takes for the temperature to increase. So we know all of this physics already. We've studied this, and let me get started with the energy. The energy formula is Q equals MC change in temperature. We know the specific heat of water, we've got the mass of water. We know that this is change of temperature in degrees Celsius, as are joules, okay? So that's the energy that is flowing into this water and heating it up. Now we could talk about the power. That would be P is energy divided by time. So that would be MC delta T divided by T. So the T here, lowercase, is time. And the new concept, so we've had energy and power before. And if you had a certain delta T in a certain amount of time, this experiment would tell you how much power was coming into that water. The third concept I'm going to write is intensity. This is a new one, but intensity, I, is just power per area. Okay, so A equals area. Intensity is power per area. So I already have the power, and I'll just go ahead and write MC delta T over A times T. And this is our, here, let's go ahead and put a box around this one. This is not a formula to memorize. This is a progression of ideas that we've already studied. So in terms of this being an experiment, we had a mass of water, we know its specific heat, we measured the change in temperature for the corresponding time that water is heating up, and this area was the area of the box there. So we can think of this as an experiment that will give us an actual value of the sun's intensity, which we call it, namely its power per unit area. And the units here, since we're using consistent units, would be watts per square meter. So yeah, think of this as an experimental setup. So I'll just write, use this formula, and these ideas is really what we're using. This formula to evaluate your experiment. And the result is the solar intensity. Okay. Result, solar intensity. Okay. And if we were actually doing an experiment like this, we might make a graph and graph the change in temperature versus the time, maybe do the data for a couple minutes or an hour, depending upon our setup there, which would still be the same results. So we're just going to leave it at this. But you can certainly try a version of this, because it's just putting water out in the sun and letting it get hot and being a little meticulous about it. Okay, having said this, I'll go ahead and give some of the official results that we get from this. So what I'm calling the solar intensity here, let's continue that with the concept of the solar constant. So this intensity of sunlight, if you do this measurement above Earth's atmosphere, say in an orbiting satellite, and it can be done in other methods than with the water, okay, but the water is the way we have learned about it. If you do this measurement, you find that I is equal to 1,340 watts per square meter. So this is what's referred to as the solar constant. This number, this amount of power per area. And I'll write here, this is above Earth's atmosphere. So we're not going to get this number in our backyard experiment by any means. Now I'm going to keep using the letter I for a number of related things. So I'll write here practically, if you're down here on Earth and not all the energy gets to Earth because some of it reflects off the atmosphere itself. So practically, I'm just going to write I is approximately 1,000 watts per square meter. And we can use this, it's a nice round number, right? 10 to the third watts per square meter. This is how much you could get if you were above the atmosphere. This, we could argue about or look up what the best value is, but 1,000's a nice thing to compromise on. So practically we've got about 1,000 watts per square meter. And you feel this when you go out in the sun, you're feeling the warmth of the sun. Even a very cold day, a wind still day, you can stand in the sun and feel that. So this power does not depend on how cold the air is around you. This is the power that's coming from the sun. That's our solar constant. Okay, so that is certainly going to be an exam question. What is the solar constant? So let me put this as a note. This is an exam type of question. What is the solar constant and how can it be measured? Well, there's the answer right there. So yeah, have this at your disposal. This is the full value. This is the practical value down here on Earth in the backyard, say. Okay, there's a couple of related things that I'm going to put up, but we'll start with that. Let me add a couple of notes The sun, of course, does not shine 24 hours a day, does it? Shines far fewer than 24 hours per day. So we can't just take this as a constant amount of energy that we're getting. We have to multiply it. Remember, power, if we multiply it by a certain number of hours, we could get the average amount of energy per day. Okay. So multiply by some number of hours per day, and then we could get the amount of energy to obtain average power or average intensity per day. Okay. And I'll give an example of that in a minute, but that's something that comes up with solar energy. You've got this number, but then how many hours worth do you actually get? Well, in the summer you get more, in the winter you get fewer, and so forth. Those kinds of things have actually been, tabulated out and measured, so you can find solar maps for different regions where say in Fresno you get a certain amount, then up there in Alaska you get more or less, actually less, right? But it's also a seasonal thing. Okay, but for our purposes, it's noon and the sun's just shining straight down and we're making our measurements. Okay, what I want to do next is talk a bit about the different applications of this, different types of solar energy that we can get now that we know that we've got this solar constant. So I will list a couple of those and go over them. I think first on everybody's mind is the solar panel that you have on your rooftop. Okay. So we'll talk about that one first. And yeah, we'll go ahead and erase all of this. Okay, so now we know how much energy is available from the sun, and we want to make use of it. That's the task at hand. And the first use is just to warm things, of course, and then the next use is direct electrical conversion. So, uses of our solar energy. And the first one, I'm just going to write direct heat / warmth. But the second one, I'm just going to put a check there. The second one is conversion to electricity, because that's become very popular in recent years, and many rooftops have solar panels on them, and some people are even involved in their in that business. So conversion to electricity happens due to what's called the photo effect. So first I'm going to write photovoltaic panels, and there's that rooftop panel. You've got sunlight shining in on it. There's our red arrow, and you've got some electrical power. Okay. So what that's actually based on is something called the photoelectric effect. So photovoltaic panels based on the photoelectric effect. Sometimes it's called the photo effect, photoelectric effect. So this is over a century old. The photoelectric effect, I'm just going to write, you've got an atom as part of a metal or a particular type of substance here. And light is not just a wave, it's also a particle. So we have what's called a gamma particle of light, and it actually strikes the atom and it ejects an electron. Okay. So an electron is ejected from an atom, and if that happens often enough, you get an entire stream of electrons, and that's an electric current. Okay. So electron is ejected. I'll just write here, ejected electrons. You can think of this as a collision. So a gamma particle collides with an atom of the right kind. Ejected electrons produce an electric current, or they comprise an electric current. And there you have it. That's why this thing works. So yeah, the direct conversion to electricity is what we're talking about when we have these solar panels on the rooftops that you see everywhere else. And what's important for our purpose now is the efficiency of the solar panels. Efficiency. And it's somewhere between 10 and 20%. I think 20% is becoming more and more common. So we'll go with the 20%. 20% efficiency. 20% efficiency means that we can get approximately 200 watts per meter squared. Okay, and this is the kind of thing that's changing as technology improves, but I think 200 watts per meter squared is a good number for a solar panel out there in the noonday sun, okay, the afternoon sun. So we got 200 watts per square meter. Now let's do an important little calculation. If I line this up reasonably logically, let's do an important calculation. How much energy are you going to get from some number of solar panels on your roof? Let's say in the day, in the summer, we have a good 10 hours of pretty intense sunlight. 10's a good round number. Let's see what we can do here. So, discussing this here, we're going to say how much energy from a rooftop installation. Rooftop installation of solar panels. Okay. There's the question. Well, energy is work is power times time. So I'm going to write W for the work. We know it's power times time. And I'm just going to put some reasonable numbers in that I just mentioned here. So the power is, let's just go with, we've got 200 watts per square meter times, and now let's pick a number. Let's say we have 20 square meters. That's already pretty large. In fact, speaking of, here are these boards. How many square meters? We've got 1, 2, and the width is 1, 2, let's say 3. Okay, so this would be 3 times 2 meters, roughly. These two boards here, that would be 6 square meters. So if you had 3 times the size of these boards, be 18, close to 20. I'm going to write 20 square meters. 20 square meters. And let's put a bracket around here because that is our power. Okay, meters squared cancel and it has watts. So So that's the power. And what about the time? 10 hours? Should we do 10 hours? That's a generous day. 10 hours. Okay. So there's our product. That's the energy. Let's see what we're going to get. 200 times 20, that's 4 times 10. 400, that's 4,000, so 4 times 10 to the third. And then we have times 10 plus 1. Okay. So the numbers themselves are just 200 times 20, that's 4,000 times 10, so that's 40,000. Okay, that's just going to be a number. But let's actually, before we do that, let's write what we have here. That would be joules. Okay. But there's another way to look at this. Namely, we have 4,000 watts times 10 hours. So we can also write that as 4 kilowatts times 10 hours equals 40 kilowatt hours. Okay, so we don't have to go through the joules, we can go straight to the kilowatt hours. And then we know what we have. This is a nice way of getting an idea what a solar installation can give you just in terms of what you're paying for, the energy you're paying for in terms of kilowatt hours. Okay, so I consider this to be a pretty important calculation, so have a good look at this. And remember, energy, power times time, and then we just went right in there. This was the intensity multiplied by an area, put it in the square bracket, that gave us the, write some notes here, that gave us the actual power. And then the time, since it was in hours, oh, by the way, I see this is a mistake. Let's go back here. I had 4 times 10 to the 3. I was so eager to get down here. I didn't actually do this one right. So let's actually do this as well. So we have the 200 times 20, that's 4,000. The hours, of course, times 10 times 3,600 because of the seconds. Okay. This would have been the joules. Okay. Got to catch the errors in real time, right? Because it's all one take and no edit. But yeah, good. So we have that in joules, but getting back to the one I really wanted to discuss, the way we can get the kilowatt hours from a solar panel installation. Okay, so in terms of this was the intensity. And this was the area. So you've got the intensity times the area, that gives you the power, and then you've got the time. So of course we can convert it to joules, but this application is nice to convert to kilowatt hours. Okay, now, so understand this. I'll try to put something like this on the exam possibly as well. So since you're doing these exams at home, of course, get your formula sheets prepared. Okay, get your own formula sheets prepared. Now, here's a point I wanted to make. With this knowledge, and it just came from our thermal physics, everything, all the way down to here, we now understand solar panels better than a solar installation salesman. I've talked to these guys before, and they need a spreadsheet. Okay, they need a spreadsheet, and then they type in some numbers and figure out what the system will do. We can figure out what the system will do just based on principle. Okay, so it's a case of a little knowledge going a long way, because you're not going to get around these principles. Sure, you can change the value of the efficiency a little bit, but these are fundamental principles. Possibly, the solar constant could be more than 1,000 down here at noon, but it's definitely not more than 1,300. So you can estimate what a big, expensive residential solar installation can deliver if you just take these ideas. Don't even memorize the formulas, you just take these ideas and start filling in the missing pieces. Okay, so that is our discussion of photovoltaic panels, also just known as solar cells, and the whole home installation. Maybe should have had a nice picture to go with it. You can make a picture of a roof, you know, a roof with solar panels on it, for what it's worth. For what it's worth, so can I. So do I still know how to draw a house? Ridge line, right, there's our house. Got a door, it's got some windows, and it has a bunch of solar panels on the top. There we have it. Okay, sunlight coming in. There's the cartoon. And these things can just be made larger or smaller depending on the number of panels, you know, scale up for how so and so many square meters. Okay, good. What's next? Okay, I'll send this up. See what we're doing for time right now. Okay, it's taking more time than I thought. That's all right. Let's talk about another method of solar power generation. This one I'm going to have you look up some interesting pictures and facts online. Okay, so we had uses of solar energy. Let me go ahead and list these again. We have the direct heat, and then our second one that we just talked about, solar cells. I'll just write photovoltaic. Okay, photovoltaic, that's the direct conversion of sunlight to electricity. And then we're going to have solar thermal. And I think it's now referred to as concentrated solar power. So we'll put here concentrated. I'll tell you where you can look this up. There are some of these installations here close by to Fresno. Okay, so the solar thermal, this is now our topic. Solar thermal. And the way this functions is the following. We have solar reflecting panels, not any kind of absorption of sunlight, but reflection of sunlight. So I'm going to write here reflecting panels, referred to as heliostats. So these reflecting panels, there's going to be a lot of board space. See if we can draw them. We've got reflecting panels. They're on a stand, and there are many hundreds of these things, and they reflect the sunlight to what's called a central tower. So in order to reflect the sunlight, say, where are we here? Say we have some sunlight coming more or less from the south, and I want to reflect it to the same point all day. These panels have to move as the day changes, time progresses. They have to move to keep reflecting the sunlight to the same point. So I'll just indicate there's sunlight coming in here, and it's reflecting off to what's called a central tower. And what is a central tower? So the central tower has kind of a tank on top. It's a big steel tower, okay? And there's the ground. So reflecting panels called heliostats, they track the sun and they reflect the light onto a central tower. There's a full many-acre field of these things. There can be hundreds, even thousands of these things. They all reflect the sunlight to a single point, which means they generate tremendous heat at this point here. Okay. So this is a solar thermal, concentrated solar thermal power plant. Concentrated solar thermal. And now the question is, what do you do with all that heat up there? A couple of possibilities, but basically you transport the heat from up here over to a normal thermal power plant, which then runs steam turbines, and then we're just talking about the heat engines, the Carnot efficiencies, and those things. So I'm going to try to draw that, and then I'll give you a heads up on where you can find out about these things, or where you can get some pictures, because we definitely want some images of the real deal on this. You're going to be amazed what's out there. See, I can't draw 10,000 of these things, but there's a giant, many acres field with thousands of these things. Okay, so what we have to do is take hot fluid up here. So what we have up here is molten salt, and it's carried in a pipeline. So I'll just imagine we have heat exchanger here. It's carried in this pipe to a tank, big storage tank. And because this was some very hot salt, this is the TH reservoir of an actual heat engine. So we have the QH going to a power plant. So I'm just going to indicate that we've got a power plant here. And you know, I'll even put a cooling tower, although you're not necessarily going to see a cooling tower next to the power plant in the ones I tell you to go look up, but in principle you can have that. So it's a power plant called Powerhouse. It's got steam turbines in there, and therefore we got to get some cooling going out of here. And you know, we could even draw some electrical transmission wires, because we're going to carry the energy out of town. Some more electrical transmission wires, and away we go. Okay, so we've got that. So from here, and this was an H, QC, and we have another storage tank with the molten salt. It's now at a lower temperature, TC. So this is our, I'll put a bracket around here, this is our entire power plant operation. And then we have to take back up to here. Could use another color for this one, but think of the direction of these arrows. The hot salt going this way, you've got a power plant. Cooler, it's still molten, okay, it's not exactly cold, is being sent back up to here. So there's a solar thermal power plant with all the shenanigans. And I'm going to have you look some of these up. And there are different scenarios, but what you're going to see is a big field of these mirrors, a central plant. The temperatures are intense. If a bird flies through this area here, it just gets instantly roasted. You may have read about that in the paper a couple of years ago. Okay, and this is the tank here. Let's make the lid fit on a little better. Okay, so there's our solar thermal, concentrated solar thermal power plant. Let's ask a couple of questions. Questions. Why concentrate the sunlight? Why is the sunlight concentrated here? Remember, several football fields or more worth of solar panels all focused on this one point. The answer is we want high temperatures. Why? Because we're running a heat engine plant. This is basically a heat engine plant, power plant, and we need the highest temperatures possible. So, because heat engine efficiency here's our answer, heat engine efficiency, and just remind ourselves of the Carnot efficiency. We want to make TH as high as possible. So that's the reason we concentrate this here. And I will put up a couple of names now, so let me just write homework. What you want to look up is Yvonne, P-A-H. This is a location on the way to Las Vegas in San Bernardino County somewhere. It's a gigantic solar thermal installation. Get some good pictures of this. Get some images. And there's more locally in Kalinga, right here across town or some miles away. Kalinga has a similar setup without the power plant. What's happening in Kalinga is, I think it's Chevron is just generating super high temperatures to get steam to help remove thick crude oil, heavy crude oil from the ground. So they're just using the direct ultra high temperatures to generate high temperature, high pressure steam to help extract oil from the ground. So you can read about both of these and more, really interesting subject. So this subject here in this cartoon, I consider to be pretty important because it's drawing a whole lot of our physics together. Remember, this is solar radiation, heat transfer, energy transfer by radiation. We reflect it into a really concentrated spot to generate the high temperatures, right? I didn't write high temperatures here, but I said it. We want to concentrate it, get the really high temperatures so that we can run an efficient heat engine complex. Something else about this, and this is real, because they store these molten salts in these giant tanks, they can actually run the thing at night. So they use it during the day, generate enough excess heat to keep running the thing at night. So as I read, Yvonne Pod doesn't run them at night, but there are some that actually have the setup to run it at night as well. So yeah, this is a major piece of information for us. Heliostats. So look that up and get some nice images. I think you'll be pretty amazed when you see what's going on there. Now, whether or not this is so important for the future is another question, because all of these solar plants, they're very, very large. They're not that efficient per se. You need a lot of area to run them, but they just epitomize all of the physics that we've been talking about all semester, so you can really understand what's going on when you see one of those things. And not only that, you can calculate what's going on as well, because now that we know about the solar constant, we could even get the efficiency of a system like this. We would need to know the total area of all of those mirrors, and then we'd have to know about these temperatures here. Then we'd get the Carnot efficiency, and we could get estimates, upper estimates on how much power can actually be generated by a given power plant. So we can do quite a bit. Okay, I think this is pretty much what I was going to tell you about solar energy. So once again, if you look back on this video, I don't have it up here now, we have well, I'll go ahead and fill it in up here. Just to summarize. So the summary of this is, for solar energy, you can orient yourself that way. We have the solar constant and how it's measured. And maybe I'll ask you directly that. What is the solar constant? How is it measured? So you have to know the different versions of this. This is the pure one, 1,340. Did I write 40 or 60? No, I don't even know. We'll say 40 watts per square meter. Okay, so we have that. Solar constant, how it's measured. Then we have the photovoltaic cells. That's the rooftop type of situation. Good to know that efficiency is approximately 20%. You take this number or the 1,000, take 20% of it and calculate things. And then the third point today was the solar thermal. And all that that entails, which is what I have on pictures. Okay, so good. I think you'll enjoy looking these things up and researching them a bit more. That really summarizes what we need to know. So take good notes, turn them into me, and we'll see you next time. One more lecture.